As discussed, crypto networks represent a major innovation in terms of decentralization and security. However, early crypto networks were highly inefficient from a user standpoint of view compared to modern payment networks. For example, the Bitcoin network processes about 5 transactions per second, whereas Visa can handle up to 50,000 transactions per second. This disparity has led to efforts for scaling up transaction throughput, hence the term scalability. How do we do this? First, sharding. Sharding is the process of splitting a database horizontally to spread the load. In an Ethereum context, sharding will reduce network congestion and increase transactions per second by creating new chains known as shards. This will also lighten the load for each validator, who will no longer be required to process the entirety of all transactions across the network. Sharding is a classic technique in distributed systems that reduce the load on the nodes participating in a network by eliminating the requirement that each node process every transaction there is. With sharding, each node instead processes only a subset of all transactions. This enables a much greater network throughput much faster, but at the cost of some redundancy. Layer 2. Layer 2 software builds upon the Layer 1 foundation, making it much more functional and composable. It inherits the properties of the layers it builds upon, yet extends the functionality of the system as a whole. An example of Layer 2 on the Bitcoin network is the Lightning network, which allows near instant transfers between two users on the Bitcoin network. The goal is to create a system that is both secure and efficient. By layering systems atop one another, it is possible to combine their individual strengths and minimize their shortcomings, because security is the most important property for Layer 1 blockchains. Much of the focus on scalability, like improving throughput, has been at Layer 2. Some examples of Layer 2 algorithms are the Polygon blockchain, etc. Decentralized applications, or dApps, are just like any other computer application, except their code is written in a smart contract on top of a programmable blockchain. This means that all of the data and logic to run the application lives on the blockchain rather than a centralized server. Because of this, no one really owns the application or the data once it is installed on the blockchain. Everybody owns it. So it is unlike any other application that downloaded from the internet or purchased from an app store. What distinguishes decentralized applications from regular applications is that they are permissionless. That means anybody can run them, anybody can join them, and they are permanent as long as the underlying blockchain itself exists. Because they are permissionless, anyone can interact with a smart contract without going through a central gateway. And since they are permanent, users and other applications will know that they will reliably exist in the future forever. This means that each decentralized application is like a Lego brick, which opens up a new world of possible applications. In the next module, we'll learn about more Layer 2 protocols such as ZK rollups and optimistic rollups.